So hello everybody, let's get settled and started. So this is Meet upcoming HBase 2.0, all right? And we'll take a look at why it's upcoming. So before that, my name is Enis. I'm a PMC member in HBase since like 2012. And I'm a previous release manager for the HBase 1.0 series of releases. This is my Twitter handle, and I'm an HBase developer at Hortonworks. All right. And so the outline of the talk is we'll take a look at the recent releases and the timelines, and a little bit look at the current repo, and then we're going to talk about versioning and compatibility and what's coming for HBase. We're going to cover what are the changes in behavior so far, and then we're going to take a look at major features in 2.0. This is the bulk of the talk, so there will be a lot of technical content here. And then we'll take a very short look at Phoenix 5.0 after this, all right? So recent releases. So first of all, a giant disclaimer is that HBase 2.0 is not released yet. And it is expected to be released before the end of year, hopefully much sooner than that. It's a community-driven work, and the initial plans obviously was targeting end of year last year, but that didn't happen, obviously. Now we are targeting end of year this year, and I think this time it will happen because there's a lot of momentum that's happening. It's also because there is a lot of changes in the current code base that stabilizing and getting everything in takes some time. But I think with the current momentum in the community, we'll definitely make this happen. And there is scheduled alpha and beta releases coming up for 2.0. So if you're interested in testing out, if you're interested in basically seeing whether your client will work, whether upgrades will work and everything, feel free to basically help us with testing the alpha and beta releases. I think the first alpha release probably will come out in a month or so. So this is the current look at the repository. If you want to contribute to HBase, which obviously you're welcome to and encouraged, this is how the current repo looks like. So as you can see, there's the master branch going on, which is going to be renamed to 3.00 snapshot, because once the 2.0 is forked, then master will become 3.0. The branch 2 branch will be the main force for doing the alpha releases and the beta releases. So the code for 2.0 will be happening from there. And we have a very active and very healthy branch 1 that's happening. And in HBase, we have a lot of active release lines that's happening and to keep the users happy, obviously. So all of these branches are corresponding to the minor releases that's happening. So the bottom one is 1.0, which we had 3 releases so far, but it is end of line. We have 1.1, we have 1.2 and 1.3. So these releases are already happening. Like from 1.1, the latest release is 1.1.9. From 1.2, it's 1.2.5. And right now, there is 1.3.1 that's happening right now. So if you're in any of these release lines, you can do a patch upgrade very easily. All right. So I also want to talk about how to choose a release if you're starting right now. And obviously, like we had all the release lines called the 9.x series. So if you're in 994, 96, 98, or anything below, please upgrade, because there won't be any more releases at this schedule. And they are pretty old, so it is time to upgrade for a newer version. 1.0 is end of line. Again, if you are in 1.0, please upgrade to 1.1 because that's the most stable release line. 1.1 and 1.2 are also very stable. You can use those to your will. And if you are starting from scratch, you have to, I think, stick with 1.2 or 1.3. And in the 1.x series, we're going to cover this as well, but moving between different versions is relatively easy, so you can actually do this without taking a downtime. You can do a rolling upgrade between releases and everything. And if you are, again, interested in 2.0, which I'm hoping that you are because you're in the talk, test out the alpha and beta releases, all right? Starting with 1.0, HBase started to adopt what's called the semantic versioning. This is a written document that it basically codifies how the releases are numbered. So it's very intuitive, and you don't have to learn anything. It's basically every release is a major, minor patch, and there's identifiers. So major means that it is 2.0.0 or 1.0.0, right? Minor means that 1.0 versus 1.1 versus 1.2. And patch release means that it is 1.1.1 versus 1.1.2 versus 1.1.3, right? So, and the idea is that between patch releases, there's only bug fixes happening. So you can very safely upgrade between patch releases. Between minor releases, there is all new features that can come in, but they're all backwards compatible. And between major versions, everything can change, right? But looking at compatibility between like different like versions and everything, it is not a binary decision. So it's not a simple yes and no, the compatibility matrix. So there is a lot of different dimensions into compatibility, and if you're thinking of upgrading between different versions, then you have to at least get a basic idea of what those are. So the main dimensions are source compatibility, binary, wire compatibility, command line tools, dependencies, and everything. And there's a lot of good documentation that's over there, and there's also other talks as well that covers this. But if you are interested in the HBase client-side interface, then we are always suggesting that you follow this API interfaces so that you would at least get the basic idea of what is guaranteed to be source compatible, what is not guaranteed to be source compatible. So the client API is explicitly marked with what's called the interface audience public annotations. So everything in the client API is basically defined by this annotation. And all of the objects like get, put, table, connection, and everything, they are the client interface of HBase. There is also limited APIs, which are usually the coprocessors or replication or sometimes filter APIs, which are also kind of our client APIs, but due to the fact that they are running inside the server-side code and they are so much tied into the HBase internals, then we have a very limited, not very limited, but we have a limited support for the guarantees that we would provide. And there is also private APIs which are marked as private or not marked at all. Those APIs means that if you're using this, anything can change between any different versions, including the patch releases, right? So this is the matrix that I copied from the book. You can just go to the HBase book and then and see this as well. So as you can see, in a major version, it says that anything can change, right? And between minor versions, most of the stuff is compatible and backwards compatible, except for the limited APIs. And between patch releases, everything is 100% compatible. That is the guarantee that HBase gives you for the clients, right? So, but what does it mean for 2.0 is that although we can break the compatibility according to our guidelines, it doesn't mean that we will, right? And we will see where we will be compatible with the 1.x and where we won't be, right? So first of all, the changes in behavior for HBase 2.0, it will be JDK 8 only. This is also true for Hadoop 3. So if you're using JDK 7, you have to upgrade. There's no other way. Basically, you shouldn't be using JDK 7 anyway, so I think that's a good move. We will have Hadoop 2.7 and Hadoop 3 support, so that is very likely. you can run between, you can choose between either Hadoop 2 series or Hadoop 3 series. There is some interface changes for filters and coprocessors for the 2.0 series. Managed connections are gone. So if you're using the old version of the APIs, you have to upgrade your client. And the target is rolling upgradable from 1.x. What it means is that if you are using 1.2, for example, you would be able to upgrade to 2.0 without any downtimes. And it also means that 1.x clients can also talk to the 2.0 servers, right, in a wire-compatible way. But there's also like other changes like upgraded dependencies and shading coming up and everything that you have to be aware of to understand the full set of changes that's coming. Some of the deprecated client interfaces are gone and removed from the source code. So if you're using it, your code will not even compile. So what are those interfaces is basically all of the interfaces on the left side. So these have been the main HBase APIs for, I don't know, 6-7 years, till like maybe 3 years ago. So HTable, HBase admin, HConnection, all of those that starts with H are gone now. So they're not all gone, but your code probably will not compile. So if you are going to upgrade to 2.0, you should start using the new interfaces on the right side. So those are connection factory, connection, admin, and table. So it's very easy. Instead of HBase admin, just use admin. Instead of HTable, just use table, right? And basically, these are available in 1.0, 1.1, and 1.2. So any release that you use from 1.x series, you would have the interfaces on the right side, okay? So 2.0 also contains a bunch of more API cleanup that we've covered some of them. There is some more, especially in the replication or security side. So again, we've basically, we are spending the effort for cleaning up the old stuff that doesn't make sense, but also we don't want to do the changes just for the sake of doing changes. But whenever we have changed something, there's usually a reason that we have changed it. And 2.0 gives us a point where we can do these kind of breaking changes because this is a major upgrade in terms of the semantic versioning, right? Similarly, like there has been leaks into our client API, leaks of protobuf and Guava methods that have been leaked into the method signatures. So those are cleaned. And the dependencies are also like cleaned up most of the time. So if you are again like considering upgrading to 2.0, you should definitely like check. First, make sure that you are using the 1.x interfaces, and then you should start compiling your code with the 2.0 releases so that you can see what has changed and what is not. And if you start doing this earlier in the release timelines, like alpha and beta releases, then you can, if we have broken something unintentionally, then you can send us a mail or open a Jira so that we can take a look, okay? All right, so rest of the talk, I'll be talking about the major features that is in 2.0, and starting with the off-heaping, and then going from there. So off-heaping, this is one of the most important, I think, features that's coming in 2.0. And the goals for the off-heaping is that regularly HBase is run with servers which has like more than 100 gigabytes of RAM and everything. And because of the garbage collection problems and the fact that the JDK7 cannot deal with large heaps, HBase wasn't able to make use of the RAM, all of the available RAM for the bucket caches and the mem stores, right? So starting with 2.0, this is getting changed on the read path as well as the write path, right? So again, like the goals is making use of all of the available memory, as well as reducing the garbage that's being created on the read path, as well as like making the bucket cache, the off-heap bucket cache, as fast as the on-heap bucket cache, right? Or on-heap LRU cache. So as you guys are familiar, probably HPAs it can be run with an L1 and L2 caches, where typically the L1 cache is the LRU cache, which sits on the heap, and L2 cache is what's called the bucket cache, where the bucket cache can be backed by the heap area or the off-heap area or the SSDs, right? And the big difference in this is that like when the heap area is off-heap, then you can allocate 100 gigabyte of your own memory in the off-heap area to HBase, and then we don't have to basically have the JVM see that kind of memory, right? The heap memory would be much smaller, which definitely helps with the garbage collection, right? So on the implementation side, normally the bucket cache basically makes it so that there is buckets of 4 megabytes in length, and then the H file blocks are basically read and put into these buckets. And if the slices are in off heap, then the H file blocks are put into the off heap area. But the problem that used to happen in the 100X series is that when on the right side, if you can see, the right side is an H file block. When the block is read from the off heap, every time a get happens or a scan happens where you're referring to the block, then we have to copy the whole block of the off heap space into the heap area. This is because in HBase, previous to this work, everything in the cell implementation was backed by a byte array, which is an on-heap data structure. So this back and forth copying from the off-heap to on-heap for every read basically ends up generating so much garbage that the off-heap advantages is basically reduced a lot. But with this work right now, what happens is that including the RPC that's happening for doing a get or scan, the cells which are sitting on the off-heap area are never copied back to the on-heap area, including that happens on the RPC buffers. So the buffers, the comparisons, and the sorting, the merge sorting, and everything happens from the data that happens on the off-heap area, and then even the socket buffers are happening on the off-heap. So there is no data copying back and forth between heap and off-heap. So to give a quick benchmark, so this is done by the Intel guys, and as you can see, this is doing a YCSP workload, if I remember it right. And as you can see, the orange one is the off-heaping read path. As you can see, there is tremendous improvement in the runtimes, right? And this is another example. This is coming from Alibaba search. So this is on the top side. What you're seeing is that they are doing 25 million QPS in their clusters. But if you can see, it is very jiggered, the graph. It's because the region servers are putting up so many requests per second that the garbage collection kicks in so frequently that even the average throughput is affected. But when they have deployed the off-heaping of the read, you can see the smoothness of the same graph in their A/B test. That this basically makes a huge difference in terms of the operational stuff, because then you don't have the constant dips coming from the garbage collection, right? So moving on, this was what I talked was mostly on the read side when you're doing a get or a scan. The work continued for doing the same kind of off-heaping, but this time on the write pad, right? So the goals for the write pad is the same thing, basically reducing the garbage being generated for every request, and then basically make HPA's region servers operationally much more smoother and getting rid of the garbage collection pauses, right? So the work actually, again, is driven by the Intel guys, and most of the work is categorized as like this. So first of all, we've made it so that the RPC buffer pools are backed by the off-heap area in a pooled request handling. What it means is that basically every time the RPC on the server side, the RPC request is received, normally we would allocate a byte array to read the RPC, and then we would keep copying this byte arrays back and forth inside the server in the write path, right? Right now, what happens is that instead of allocating a big chunk for reading the RPC into a byte array, right now we are doing we allocate a bunch of off-heap pool areas, and then off-heap buffers in a pool area, and then we are reading the RPC request into this. So the same pools are getting reused over and over, and we don't create any more objects for reading the RPCs, right? Then we've done the work for reducing the garbage created by the codec and what's called the MS lab copying. We won't go into details of those, but if you catch me offline, I'll be happy to talk about the details here. But the other work is that what's called the MS lab is normally used for heap fragmentation on the on-heap side, but now we've made it so that the MS lab can also allocate buffers on the off-heap area. So similarly, what happens is that the RPC request, if it's a big writes, which are coming from puts and everything, then the cells are copied into the off-heap area, and then they are basically allocated there, right? So this gives us a lot of benefits together with the read pad. Right now, the read pad and the write pad allows us to basically have the region server to have a much bigger total mem store space, as well as much bigger RAM usage, right? And normally, like again, as we talked, the cell data goes into the off-heap pad, and the cell metadata, which is like the concurrent skip list map entries and other overhead, is still on the heap area, right? So we still need to keep track of what is the cells and everything. But this metadata is comparatively very small compared to the actual cell data. There's also other work which happened for what's called the async wall. So normally, this is a little bit technical, but normally in HDFS, if the write-ahead log is based on HDFS, normally for writing the writes to the write-ahead log, we would be using the HDFS's output streams for copying the data, and this work is also doing the thing where from off-heap we don't have to necessarily bring the data to the off-heap, on-heap, so that we ship it to the HDFS client. So the async wall is basically a way to accomplish that. And this thing also works with the new compacting mem store. We'll come to that a little bit later. So this is just a basic benchmark, again from Intel. As you can see, it gives very nice benefits in terms of the write speed. But mostly the benefits are not just improvements on the speed, but basically making it so that things are running more smoother over time, right? So coming to what's called the compacting MEM store, this is a work that has been driven by Yahoo Research, and this code is mostly complete. So what it is that normally the MEM store is a concurrent skip list map. So what it means is that basically every cell that you write goes into the skip list map. So there is definitely a lot of overhead in the concurrent skip list map implementation, because in a single region, let's say your flash size is 128 megabyte, you can end up with like millions of cells in a single 100 megabyte entry, right? So in your skip list map, every time you want to access something, the index is so big, including like hundreds of thousands of entries, that like the overhead from the skip list map becomes a big problem. So what the compacting MEM store does is that we have what's called an in-memory flush and in-memory compaction, okay? So basically, in-memory flush is used to reduce the index size. That's happening only in memory, right? And the in-memory compaction is also reducing the index sizes, as well as eliminating the duplicates. So these flashes and compactions are different than what's happening on the disk, what's called the regular flashes and compactions, right? These are happening only on the disk. Here is a diagram. So I don't have the time to go into all of the details. There's a very good talk you guys can go check in YouTube if you're interested in this. So basically, the main idea is that you have a concurrent skip list map in the top, and then you would be basically doing in-memory flashes and creating immutable segments only in memory. And then you're, from time to time, you're compacting these immutable segments into other immutable segments. And that also happens in memory. And when you're running out of memory, then you flush to disk, which creates a new file and everything. So this is basically transparent to the client and everything. But this is what happens internally, right? And this is an illustration of what's happening. So at the top, this is at the top in the pink box, you can see that is the concurrent skip list map, which has a lot of overhead per cell. And when you basically flatten it, then it becomes an array of cells. And then the gains are basically you're compacting your representation in memory for a bunch of cells so that you don't have to go to disk a lot of times. All right. Moving on, so region assignment is another area that actually is getting now a lot of improvements and everything. So traditional region assignment has been one of the pain points in HBase. It was, if you guys have run HBase clusters, region in transition is a very common thing that you would see. So the idea here is that basically we would want to get rid of the region transition problems once and for all. So basically, the idea is to use the internal, what's called the procedure V2 framework for doing the region assignment itself. So procedure V2 is already active in 1.1 and afterwards. So every time you do a DDL statement, like create table, alter table, and everything, it runs in the procedure V2 framework. And what it is basically conceptually it's very simple. It is every operation is broken down into a series of steps in a state machine, and every time you do an operation in the state machine, you basically save the state before you do the operation. You save the state of wherever you are left with in a durable storage, right? And in this case, the durable storage is a write-ahead log on HDFS. And then the beauty of it is that basically, since you're doing you're basically breaking up the operations into distinct steps, and then you're basically saving each step whenever before you're doing it as a write-ahead log, right? So if a master dies in between when you're left in the third step, then the backup master basically can recover the state fully, and then keep on basically rolling forward or rolling backwards the work, right? So basically, the idea is to use the same mechanism to do the region assignment. All right, moving on. So the other area that saw a lot of work is the asynchronous client. Asynchronous client is basically different than what's called the OpenTSTB async client. So OpenTSTB async client has been around, I think, for maybe 5 years or something. But this work is completely independent of it, as well as this work is basically living inside the HBase code base. So once 2.0 is released, we would have both a synchronous client and an asynchronous client supported at the same levels, right? And it is driven by the Chinese folks and includes most of the critical functionality. I think, like including the admin, DDL, scans, gets, writes, everything, including coprocessor calls and everything. I think most of the stuff is there. Only like some very advanced functionality is not there, like read replicas and everything. All right. Here is a code. This is Java 8. Again, you will love it if you see it. So this is how you do an asynchronous request, right? You create an asynchronous connection. Instead of a connection, you do asynchronous connection. Instead of table, you do async table. And then you basically, you do a bunch of puts. And then the puts will return you a Java 8 feature. Then you can attach a lambda to the return features, and then you would basically do the gets afterwards. So it's basically super easy to program because they are returning Java 8 features, and then it's also like pretty stable right now. All right. The next thing is the C++ client. So this work is going on. Which for doing a native C++ client, this won't use REST API or Thrift interface or anything. This client goes directly to the region servers and talks at the same binary protocol that the region server talks to, right? So it is developed using the C++ 14 standard. So if you're using anything else, you can compile, sorry. But C++ 14 is an amazing standard. We cannot basically use anything else because of the smart pointers and all the advanced functionality. The architecture is done so that it is a synchronous client, but it is built fully on the asynchronous client. So there is no asynchronous client API yet, but doing that would be relatively very little amount of work. It uses Foley and Wangle from Facebook. It's like Netty, and it gives you like Java 8 kind of feature. So this client looks very similar to the async client that we've talked about, right? And basically, right now, gets, puts, and multi-gets are working, and scans are coming. Next. Here is a code example. Again, we won't have the time to go into details, but you would generate a configuration similar to the Java world. You would open a client. You would open a table. Then you would do puts, and you would do gets. So the API looks similar to the Java APIs. There's like puts, tables, connections, and this and that. But this is fully on the C++ side. Moving on, backups and restores. This is also a very interesting feature that's coming up. So HBase needed a reliable backup mechanism for some time. And with 2.0 right now, it is coming. If you look at the current options, you can, in 1.x, you can do snapshots, you can do replications, but you cannot do backups, right, end to end. So, and snapshots, backups have different guarantees. But in the end, what you have to do is basically you have to use replication as well as backups for managing your data, right? So the work basically makes it so that there is full backups as well as incremental backups. And you back up to a remote file system. And that file system can be an HDFS file system. It can be S3, ADLS, WASB, or any other Hadoop-compatible file system. So if Hadoop has a driver for that file system, we can basically make use of it to back up over there, right? The full backups are based on snapshots. There is no new work for doing the backups. It is a take a bunch of snapshots and export it to the other location. Incremental backups, on the other hand, uses what's called the write-ahead logs, right? So basically, once you take a full backup, then you can take daily incremental backups, where every time you basically take an incremental backup, we give you a bunch of write-ahead logs so that you can replay it back. And backup and replication are definitely complementary solutions, right? So on the restore side, we have a very flexible restore options. So you can basically restore to the same table. You can restore to a different table. And basically, you can either write your own MapReduce job to do a custom restore, right? So basically, on the restore side is very flexible. So for example, if you run into a problem where you're OK with overwriting the data, you can just restore to the same table. If you want to recover a very small amount of data, you can restore to a different table, but then do a selective copy table, right? Or selective copy. Or basically, you can, as I said, you can restore using a custom tool set, right? Moving on, file system quotas is, again, another feature that's coming up. HBase normally supports quotas in 2 different levels. There is like request count in terms of like you can do this many requests per second and everything, kind of quotas right now. And there's like number of tables, number of regions in a namespace kind of quotas. So this work enables setting quotas on disk usage. So you can actually set quotas per table or per namespace of the actual disk space usage that this table or this namespace can get. So this definitely helps with the multi-tenancy, where like you can say, okay, if you're tenant X, you have to use this namespace, and you cannot grow bigger than 100 terabytes, right? So, but there's obviously the questions of what happens if you actually run into your quota, right? That is the violation policy, where it will say either disable, no writes compactions, no writes, no inserts. So since HBase, the deletes are tombstones, right? The problem happens where, like, if you, for example, disable all writes and deletes, then the tenant, once they're over their quota, they cannot delete the data, right? Because deleting actually is writing more data. So it increases the disk space usage. But with the violation policy settings, then you can choose as an operator what to do based on different policies, right? Again, we don't have the time to go into details, but you can go into this JIRA 16961 if you are interested in this. So basically, in the below, this is how you would set the violation policy and everything, and then the other thing that I would like to mention is that with the snapshots coming into picture, the quota settings is becoming a little bit more complex, because obviously the snapshots also can take some space. So what we do is that the snapshot usage is counted against the actual originating table, all right? So moving on, there is some stuff that hasn't been released in Apache yet, but some of these have been released in other distributions like HTTP or CDH. So, but on the Apache side, these will be released the first time. Medium object support is one, region server groups is second, favored nodes is third, HBase Spark module is also coming. Write data logs and data files in separate file systems. This is also very exciting. And there's a bunch of other stuff. Netty server, Netty client, API cleanup, replication improvements, Matrix API, Matrix for corpuses, and a bunch of other stuff that's happening, right? And this is the last slide. So again, Phoenix is usually very tied to HBase. And Phoenix project itself also has a major release, what's called the 5.0, and it is expected in the similar time frame for, this should have read HBase 2.0 anyway. So it is expected in the same time frame, and basically it will probably support HBase 2.0, at least we are working on it. So once it's released, it will be supporting the 2.0 clients as well. It is rewriting the internals using what's called the Apache calcite. And basically, the SQL parser, planner, and the optimizer comes from calcite. And the calcite has a very nice cost-based optimizer that's being used by Drill and Hive. So, and basically, what calcite provides is the default rules with a pluggable engine, and Phoenix specifies its own rules, okay? And obviously, calcite has much more SQL support. All right, so thanks for listening. So if you, sorry, we didn't have any time for QA, but if you catch me offline, I'll be around. And after this, there's also Lars George's talk for HBase, so stick around.